All right, what's up, everybody? Hear me? Good? Thumbs up? Excellent. Okay. Right, so today all we're going to be doing is doing some review for our exam on Thursday. So we just got some chapter 18 and 19 material to review, as well as some stuff that I just wanted to remind everybody that we actually first touched on in chapter 8, but has been pretty relevant for this chapter as well, and this is this concept of aromaticity, right? So we want to be able to recognize whether something's aromatic, anti-aromatic, or non-aromatic. Something we first talked about again in chapter 8, so we'll do some review on that. First things first, let's just start off with some nomenclature, all the different benzene compounds, right? That was sort of how we started this guy off. So everybody take a second, and this is basically just what we're going to be doing today, is chugging through problems. I'm going to put them down on the screen, give you guys some time to answer them, go back through and give you the answers, etc., etc. All right, so yeah, starting out with nomenclature here, just tell me what all these different compounds are going to be called. I guess really quick, let me just also interject. Tonight, right, we got the homework for the lecture due, as well as, I think more importantly, or at least a bigger amount of work, is the formal that's going to be due. This week we'll be doing experiment 51. Yes, I was in the lab yesterday and was incredibly unsuccessful at this, but luckily found another video of somebody else doing it, not at the micro scale, but at a macro scale, but it still follows the procedure pretty closely. So anyway, I'll post those later today. I was thinking about going back today and redoing it, but the chlorosulfonic acid is terrifying. You open it up and it's like a bubbling cauldron of noxious gas. So I'm gonna let this other lady on YouTube take care of it.
I actually don't remember that. What does anti-aromatic mean again? You're muted.
bad. That's when it meets all the rules. Wait, was I muted for that whole spiel about the lab?
Yeah, the whole time.
Okay, great. Awesome. Okay, I'll redo that. Anyways, yeah, so Anti Aromatic. So review from chapter 8, but basically Anti Aromatic is when you meet all the rules of what you should be for aromatic, meaning that you're flat, you got a network of sp2 orbitals or pi orbitals all lined up, or rather p orbitals all lined up, but you don't have that 4n+2 number of electrons. So yeah, I mean, I realize that this is probably something that we haven't thought about too much in a while, so we'll review all that, and I'll do my whole spiel about what I said about the lab here in a second.
We heard the part about the lab.
Oh, okay, okay.
Yeah, it was just when I asked the question.
Okay, cool. All right, so let's go through these nomenclature ones. What's the first one going to be?
Chlorobenzene.
1-chlorobenzene.
Chlorobenzene. Yeah, and just like if it was cyclohexane, you don't have to say 1-chlorocyclohexane, because if there's only one substitution, we just assume it's at position 1, right? So this is very similar to the nomenclature that we've seen, except for now this benzene is our parent chain, so that's what's going to come at the end. That is, as long as you don't have some sort of special exception where it's given its own name. So we'll see that in a second. So now we have chlorobenzene here, but we got this methyl substitution. So this is going to be...
I got 4-chlorotoluene.
I would accept it, but really 4-methylchlorobenzene. For whatever reason, toluene is one of the ones that, like, we call it toluene when it only has one methyl group, but we don't use that as like a parent chain from there on out. Honestly,
Gotcha.
I
Okay.
think it's stupid. I would have given it to you, but yeah, it is one of the weird ones. Unlike, you know, phenol or something like that, where you would be right. It would be 4-methyl phenol. All right, but that brings us to this one, which Eric is correct. This guy is toluene. It's got its own special name when you got 1 methyl group. What about when it's 2 methyl groups?
1,4-dimethyl-benzene.
1,4-dimethylbenzene is perfectly acceptable. 1,4-dimethylbenzene. However, if you were to walk into the back into the stockroom, you would never see any 1,4-dimethylbenzene. This guy also has a special name, and this is xylene. So a xylene is a benzene that has 2 methyl groups. And then, you know, this is sort of a common name sort of thing. So you would indicate where its position was using that ortho, meta, or para nomenclature. And so which xylene would this be?
Para.
Para, yep.
Para.
So this is paraxylene. Or really, if you saw it on the back, it would be p-xylene written on the bottom, on the bottle rather. Okay, so then these 3 all have sort of special names that become their own parent chains. What's the first one?
Phenol.
Yeah, so this guy is phenol. And what I mean by they become their own special like parent chains is if we had, for example, an ethyl group in this position, this would now be 3-ethyl phenol. Right, the phenol itself, that benzene ring with the OH group becomes the parent chain. Also, meta-ethyl phenol would work. What about the next one?
Aniline.
Aniline. One that's actually pretty important just because in throughout chapter 18, we learned like a ton of different stuff that you can do starting with aniline. All right, so we'll do some of those reactions today, but I feel like it takes a bit more of a central role than some of these other guys. And again, it becomes sort of a parent chain. So if there's a methyl group right here, what is that going to be?
Orthomethyl-aniline.
Yeah, ortho works, or 2. Right, the difference being that the ortho-para meta or ortho-meta-para, those are sort of considered to be common names. You see them all the time because, again, we do actually refer to the benzenes with their common names, but it's not wrong, and it's in fact the IUPAC way to use the numbering system. What about this guy? We've actually used him a bunch in lab.
Benzaldehyde.
Yeah, so this is benzaldehyde. All right, of course, we have an aldehyde group attached to our benzene ring. And this other one we also used a ton in lab.
Benzoic acid.
Yeah, so this is benzoic acid. And again, what if I had, let's say, an iodine group right there?
Meta-iodo benzoic acid.
Yeah, meta or 3-iodo benzoic acid. All right, and then the last one, this group plays like a significant role in this chapter. We've seen it a few times, but never like used it and abused it as much as we did in the past few weeks. This is
Nitrobenzene.
yeah, so this is a nitro group. So this is nitrobenzene. Okay. Aromatic, anti-aromatic, and non-aromatic. So first of all, I think, well, let's actually just focus on these 3 right here because they're like the best example of what of the 3 different ones that we have here. Okay, so again, first of all, you want to sort of rewind in your mind back to chapter 8. This is the particular slide in chapter 8 that I'm talking about. And this is where we sort of learn these rules for being aromatic, anti-aromatic, or non-aromatic, right? The most important thing about an aromatic two most important thing about an aromatic compound. Let's actually take a look at, where is it going to be? Take a look at this picture here. One of the most important features of an aromatic compound is that they have this network of p orbitals all lined up right next to each other, right? Because this is the whole shtick about what it means to be aromatic are these electrons are sort of sharing through resonance this entire network of p orbitals. So you have to have them all in a line, all in a ring sort of thing. You can have multiple rings stacked together, but the most important thing is that you have those p orbitals available. Okay. If you don't have those p orbitals available, so for example, if one of these carbons, instead of being sp2 hybridized, was sp3 hybridized, then that would be considered non-aromatic. Okay. So if we look here, one of these three in this red box here is non-aromatic. Which one's that going to be?
The one on the far left?
Yeah, why is that?
Because it has an sp3 carbon.
Yeah, absolutely, right? So the thing that messes this one up is this carbon right here is sp3 hybridized. So there's no p orbital sticking up that can sort of participate in that resonance network. So this is non-aromatic.
So any ring that has an sp3 carbon is non-aromatic. It doesn't matter
Correct.
where it is.
Yeah. I mean, if it's interrupting that networks, yeah. I mean, I can't think of an example where you could still be aromatic and have an sp3 carbon there. If it's outside of the ring, then that wouldn't mess it up. But yeah, if it's in the ring, it's gonna mess everything up. Okay. So now the other key rule, so that sort of differentiates our non-aromatic compounds. They don't have that network of p orbitals. So now aromatic versus anti-aromatic. This has to do with this 4n plus 2 rule, okay? Which another way of, and again, you know, like this whole problem of what is n arose. Remember, this is just a shorthand of representing a series of numbers, either 2 when n equals 0. So n equals 4n plus 2 equals, so if n equals 0, 4n plus 2 is 2. If n is 1, 4n plus 2 is 6. 2, 10. 3, 14, et cetera, et cetera, et cetera. All right, so that 4n plus 2 is really just a shorthand for a series of numbers. If you have this number of electrons, either 2, 6, 10, 14, then you are aromatic. If you don't, if you just have a 4n, you know, it's always going to be even, right? Because they're pairs of electrons. If you have 4 or 8 or 12 or 16, that's when you're anti-aromatic. Okay, so one of these two compound, right? So we already got this one's non-aromatic. One of these is aromatic. The other one is anti-aromatic. So see if you can take a second to figure out which one would be which.
What exactly is n?
So n can be anything, right? Or, well, n can be any integer. N is either 0, 1, 2, 3, right? So here's my n values right here. And it tells you the number of electrons that are allowable, right? So this 4n plus 2 is a shorthand for this series of numbers here. 2, 6, 10, 14, 20? No, I lied. Sorry. I can't do math. 18, etc. All right, so which one of these guys is going to be anti-aromatic? All right, I guess let's start with which one's going to be aromatic.
The one on the far right is aromatic.
So this guy's aromatic. And again, it's because the number of electrons will follow this 4n plus 2 rule. So let's just convince ourselves of this. We have 2, 4, 6 electrons in pi bond, or in p orbitals there. So 6 is one of our numbers in this series. Right, so if you have 2, 6, 10, 14, 18 electrons, et cetera, you will be aromatic. If you have on the converse anything else, then you're anti-aromatic. So that would take us to this here. Since this is a positive charge, let me get a different color. Since this is a positive charge, that of course doesn't represent any electrons. That's an empty p orbital. So this has 2, 4 electrons. That's not one of our numbers in our 4n plus 2 series. So this is anti-aromatic. Okay, so non-aromatic meaning that you don't have that network of p orbitals. There's some sp3 hybridized atom in there. Anti-aromatic is you don't follow the 4n plus 2 rule. Aromatic is you do follow the 4n plus 2 rule. All right, so let's zoom back out. Everybody take a second and finish up these compounds for me. All right, so what do we got for benzene?
It's the aromatic compound.
The aromatic compound, absolutely. If you know anything to be aromatic, that's an important one. All right, and again, we can just prove this to ourselves, right? Each one of these carbons is sp2 hybridized, awesome. And then also importantly, we have this 2, 4, 6, right? So this follows our 4n+2 rule. Again, the 4n+2, I think that when people see it, they think a math equation, like we're trying to solve for 2. That's not what it is at all. It is a shorthand for a series of numbers. 2, 6, 10, 14, 18, etc. You could take it all the way to infinity. Honestly, you'll never have to go past 18, but yeah. So then what about this guy here? Now we have 2 benzene rings that are sort of connected together.
Well, they're all sp2
Anti Aromatic.
hybridized.
Yeah, awesome. So first of all, like first check, every single one of these carbons, you can go in and convince yourself are indeed sp2 hybridized.
So you know it's not non-aromatic.
So it's not, so we can cross out non-aromatic, right? We got that network of p orbitals, awesome. But then I believe it was Sam that pointed out that absolutely we have 2, 4, 6, 8, 10, 12 electrons, right? This does not satisfy our 4n+2 rule. So that makes this anti-aromatic. Okay. Now our next examples are all going to involve these heteroatoms. What makes that a little bit more challenging is because they can have pairs of electrons that may or may not contribute to the ring, right? They will contribute to the ring if it makes it aromatic, but they won't if it doesn't. Okay, so let's look at this example here. This is again, who?
Azacyclopentane.
And
That was pretty good, but no, because it's got these double bonds, we call it something special.
like diaphrone or something.
Pyrrole?
Pyrrole.
Pyrrole.
That's up to 2 R's. Pyrrole. All right, so just like benzene has its own special name, pyrrole has its own special name. So if we were to stick a chloro group right there, for example, this would be 2-chloropyrrole. Pyrrole is one of those words that you just gotta know. All right, so let me get rid of all this. Let's take a step back here. All right, so now we got pyrrole. First of all, we got to make sure that everything is, as we would expect in terms of hybridization. So first of all of these carbons are pretty easy to figure out that they are indeed sp2 hybridized. Check. But what about this nitrogen?
It's also sp2.
Yeah, so it is in fact also sp2, but let's just look for a second. First of all, how many lone pairs do I have on this nitrogen?
Just one.
One lone pair, right? So normally with a nitrogen that has 3 bonds and a lone pair, we would expect it to be sp3 hybridized.
Mm-hmm.
Okay? But this nitrogen is specifically not sp3 hybridized so that these electrons right here can participate in this ring, right? So we saw sort of specifically for pyrrole, its electronic structure looks like this, where my nitrogen is sp2 hybridized, and that lone pair of electrons is what's living in that p orbital solely so that it can make this compound aromatic, right? Solely to participate in that network of p orbitals rather. I keep on wanting to say pi. So now we have 2, 4, 6, everything's sp2 hybridized. So pyrrole is another classic example of, of an aromatic compound. All right, like hint, hint, nudge, nudge, all the special ones that we learned about are aromatic, but we'll go through and prove this to ourselves. But what about when we have a protonated pyrrole?
That's
Anti-aromatic.
sp3, so it's anti or non-aromatic.
Not.
Who votes non-aromatic? And who votes anti-aromatic? Okay, so Now we have a nitrogen that has 1, 2, 3, 4 bonds. So this nitrogen has to be sp3 hybridized, making this non-aromatic, right? By forming that new bond, it takes away that pair of electrons that used to be able to contribute to the ring, and now it doesn't have that sp2 hybridization. This was another special one that we learned about. Does anybody remember its name?
Pyridine.
Yeah. This is another one you just got to know. Pyridine. How many pairs of how many lone pairs are on my heteroatom?
8.
1.
Right, so this nitrogen has this pair of electrons. I specifically didn't draw it in, so we got to figure out the hard part here. And now, is this going to be aromatic, anti-aromatic, or non-aromatic?
Aromatic.
So it is aromatic. Let's go through and convince ourselves of that real quick. All right. Aromatic, they're all sp2 hybridized, and I got 1, 2, 3 pairs of electrons, or 2, 4, 6 electrons, so that follows my 4n plus 2 rule. Notice how I don't include this pair of electrons, right? Nitrogen's already got a double bond here. So this pair of electrons must live in an sp2 hybridized orbital, not in that p orbital. Remember, a big part of this chapter, sort of like qualitatively, were the shapes of these molecules. We sort of specifically looked at pyridine here and its orbital structure. There should be a 2 here. It already has a pair of electrons that's contributing to that double bond in a p orbital. So that means that the lone pair has to be living in an sp2 hybridized orbital.
And it doesn't contribute, so therefore it doesn't
can't
contribute to the ring.
right? You can only contribute if you're in this little circle of p's here. Okay, so then we go over to the protonated pyridine. Is that going to be aromatic, anti-aromatic, or non-aromatic?
Anti.
Okay.
1, 2, 3.
Oh, it's still aromatic.
Boom, nice. Carlo, awesome.
Wow.
It is still aromatic, right? So I did this specifically to point out the difference between pyrrole and pyridine. Because in pyridine, that pair of electrons wasn't involved in that resonance network in the first place, occupying it with a hydrogen doesn't change anything. It is still an aromatic compound. You still have your 2, 4, 6 electrons contributing to the ring here. All right, and so take a second and do these last 2. We should actually be able to name this one as well.
Furan.
Yeah, nice.
Thank you.
Say that "an" in like a more country way, so it's furan, but yeah. Or furan, I don't know.
Does the oxygen act like the nitrogen and not its electrons don't participate?
So that's a good question. So first of all, how many pairs of electrons are there on this oxygen?
It has 2 lone pairs, but one of them are p electrons.
Yeah.
Or whatever.
So Carlo, to answer your question, they'll participate if they can and they make it aromatic. But in the case of like the nitrogen here, so let's just take a second and compare pyrrole and pyridine. Right, notice the difference between these 2 nitrogens. The nitrogen in pyridine, this guy over here, it already has a double bond. So it's already got a pair of electrons in the p orbital. So that means that our lone pair can't be in a p orbital. Different from pyrrole, where there is no double bond, So that's why that pair of electrons, this guy right here, is allowed to be in a p orbital. So then Eric's exactly right. When we go down here to furan, you actually have one pair of electrons, right? So we have this pair of p electrons, this pair of p electrons. These guys are all in p orbitals. But that means that this pair of electrons is not. It's going to be in an sp2 orbital. And again, we saw sort of earlier in this lecture a more detailed picture of what that looks like. Oops. Down here, right? So here we have one pair of electrons that are in that pi cloud and the other one that isn't. And then what about the next compound here?
Non?
Yes. Why non?
It doesn't have all open p orbitals?
Yeah, absolutely. This guy right here is messing everything up, right? This carbon right here is sp3 hybridized. That just sort of shatters that whole network.
I can't remember what the name of that one is, though.
So this is going to be 2, 3, 4, 5, 2, 5 oxacyclohexene. Oxacyclohexene.
Hexene.
Maybe even hexadiene. Yeah, 2,5-oxacyclohexadiene. All right, because the oxygen gets 1, so that means 2, 3, 4, 5.
One question I did have, whenever we learned about the oxa and azacyclo compounds before, they had they were like carbonyl groups, weren't they?
Right, because they were all preceded with a 2-oxo. So they were 2-oxo-azacyclo or 2-oxo-oxacyclo.
Oh, gotcha.
And that 2-oxo represented that ketone group.
The ketone. Okay, gotcha.
All right, so now everybody look in the chat. We're just going to practice, make sure we're all down for the exam. It's the exact same as we did last time, but let's just go through it. There should be a link that you click in the chat. That'll download a question, and then you're going to answer it and upload it to Canvas. So let's just go through that process right now, make sure we all got things down, and I'll put up another problem on the screen while you guys do that.
It says the file is locked.
Yes, it should be, but you should be able to add, you click the right link.
Yeah, Monday, Wednesday.
Yeah, mine is telling me it's locked too.
Gosh, bless it. All right, give me a second.
Tuesday, Thursday. Locked as well.
Yeah, it is locked. My bad. Hold on. Let's try this again. So Monday, Wednesday. That's for you. Tuesday, Thursday, that's for you.
All right, mine is submitted.
Cool. I'm going to check them at the end, and I'll let you guys know if there's a problem. But we're actually running short on time relative to what I thought, so we got to move a little bit quicker.
Are we doing? Are we submitting these problems that are showing currently, or just the one problem that
No,
was?
and no, you're not submitting these ones that are shown currently. And really, I just wanted to get everybody to practice the submission process again. It's not like I'm going to be grading even this example problem or anything like that. I just want everybody to have the motions down for when we do the exam next class. Should be the exact same strategy that you did last time. I just want to make sure we're all clear. All right, so then these problems that are up currently, these are all sort of reduction type problems. Yeah, I mean, in particular, let's look at these first two real quickly. Let's look at actually this second one here, because this is what we learned from a previous chapter. What happens when you reduce a ketone? What do you get?
An alcohol.
An alcohol group, right? So here, this would reduce, well, I guess there's a hydrogen there, so I don't have to draw it. So this would reduce to this secondary alcohol here, okay? And that's just using our normal old hydrogen gas and palladium catalyst. When you have a carbonyl group that's located directly next to a ring, right? One removed, what do these reducing agents actually do?
They take off the oxygen?
They chop it off altogether, absolutely. So here, you get reduced to propylbenzene, right? This is only the case when those carbonyl groups are located directly next to the ring. Okay, so now let's look at these two examples here. Now I have two carbonyl groups. Like we said, if we only want to remove, oh, I guess this would actually reduce this to that was a bad example, my bad. This would reduce this to an alcohol group, but it wouldn't chop it off completely. So if we wanted to only remove that carbonyl group next to the ring and then reduce the other one, I guess we could oxidize it again back to a carbonyl group if we wanted, but yeah. Then we could use this palladium catalyst. We did learn of now a new special reduction method that would remove both of them no matter the proximity to the ring. Does anybody remember what this is?
Is that the N2H4?
Yeah.
Negative OH.
Yep, absolutely. So this is what was called the, who is this dude? Wolff-Kishner. But yes, this is using this, our H4N2, whatever, OH minus, and heat. That will remove any oxo groups, right? Any carbonyl or aldehyde groups can be chopped off through that method. All right, so I just these are just two reduction techniques that we learned. Because it is a difference with this palladium catalyst with what we have seen thus far, I wanted to make sure to bring that to everybody's attention. All right. So I'm going to come up with another sort of synthesis type problem here, but I want everybody to take a second and make sure that you can draw me the various resonance structures for this type of compound here and identify whether it's electron donating or electron withdrawing. Okay, resonance structures are another thing that we first did in chapter 8, but they're not going away in this chapter, right? Any conversation about aromaticity is going to necessarily involve them. So make sure you know how to draw resonance structures. And again, just to remind everybody, at the end of chapter 8, there's like a worksheet, like a few pages in the book that are dedicated to drawing resonance structures. All right, so just taking a look at these resonance structures. And again, this guy is who?
Aniline.
Aniline. So these are the various resonance structures. So is aniline going to be an electron donator or an electron withdrawer?
Donator.
Right? I mean, as you can see, it's donating electrons to the ring here. Furthermore, you can convince yourself of that because you have this negative charge bouncing around your ring, right? So it's going to make that ring more nucleophilic, okay? And then what type of a director is an amine group?
Orthopara.
Orthopara. So notice here also that negative charge is bouncing around to the ortho and the para sites. It skips right over that meta site, right? So that's why those carbons are that much more nucleophilic, right? So this is an electron donating group. It will activate the ring, meaning it will make it more reactive to this type of electrophilic aromatic substitution, and it will direct to the orthopara position. Okay. So again, this is we were talking about electrophilic aromatic substitution reactions. Who's the nucleophile in electrophilic aromatic substitution reactions?
Benzene.
The benzene ring, right? If it's an EAS, that means benzene or the ring is nucleophile. Okay. So first of all, let's ignore these two guys for a second and just compare benzene with aniline. Which one's going to be more reactive?
Aniline?
Aniline, right? So just like we saw before, now you have this negative charge bouncing around that ring. That means that that ring is an even better nucleophile, right? So in this case, in terms of EAS reactions, aniline is even better than benzene, right? If you have electron donating groups, they will make it more reactive because they'll make it a better nucleophile. All right, but really we want to compare these different heterocyclic compounds that we learned about here. So again, this guy's benzene. Everybody knows him. What's this next one?
Pyridine.
Yeah, so this one's pyridine. And what about the last one?
Pyrrole.
Also
Pyrrole.
Pyrrole. Which one of these is going to be the most reactive with regard to the electrophilic aromatic substitutions?
Benzene.
What is it?
Benzene?
It's not benzene, no. So one of these guys is actually going to be more reactive, and that is pyrrole. What did I say? Increasing reactivity? Okay, so you can go over here. So what we learned is in terms of these electrophilic aromatic substitutions, pyridine is the worst, whereas pyrrole is the best, right? That nitrogen can act as a sort of donator to the ring. These are even better nucleophiles. And what if right, there was another reaction type we learned about, not electrophilic aromatic substitution, but
Nucleophilic aromatic.
Nucleophilic aromatic substitution. In nucleophilic aromatic substitution, benzene is the
electrophile.
Yeah, I mean, the ring itself, yeah, one of the carbons in the ring is an electrophile. If we're just gonna, quick rules to remember here. And so then this is going to have the exact reverse reactivity. Now the pyridine is more reactive to these nucleophilic aromatic substitutions, and pyrrole is the worst for the nucleophilic aromatic substitutions. Remember, these all require you to have some sort of a good leaving group on the ring as well. It doesn't just work with a naked benzene. There has to be a leaving group there for the nucleophile to come and kick off. All right, so now just going through the reactions, we're sort of not starting off easy here, but again, just want to sort of get in as much as I can in this time frame. I think that this is one of the more important reactions to remember here, and this is when you take aniline and convert it to something that does have a good leaving group, right? Because what I need to do is I need to swap out this aniline for this, or this amine group for this hydroxyl group right here. Unfortunately, this is a terrible leaving group. So we can treat it with something that makes it a banging leaving group, and what is that? Anybody?
NaNO2, HCl.
Yeah, so HNO2 and HCl. Do we need heat? No, actually, no. It's got to be 0. And this will convert this to what's called a diazium benzene, right? This is now this guy, diazium group. And this is a really good leaving group right here because it will eventually pop off as nitrogen gas. Okay, so this reaction right here, very important in order to convert this aniline, this amine group, to a good leaving group, which then I can treat with any number of nucleophiles to replace in an NAS type reaction. So there's two ways to, so first of all, let's now focus on this one and this one here. There's actually two ways to make alcohol groups, or a phenol rather. One of them, the simplest one, is just acid and heat. All right, so if you're gonna memorize anything for sort of like multi-step synthesis type reactions, that's gonna be the easiest one. But there's another way that we do this that's actually a higher yield. So in practice, we would do this. Does anybody remember what that involves? So this is this copper 1 oxide. Okay, again, I don't know that you want to memorize that for a multi-step synthesis, but seeing it in a like one of those like reaction webs, you should know what this does. Okay, and again, this is a way to replace this diazium group with an alcohol group. You need some other, and H2O. Okay, but again, when you see that copper 1 oxide, you're sort of thinking alcohol group. Okay, so let's see if I can't clean this up a little bit. Everybody take a second and see if you can't tell me what happens in this reaction.
The zonium group is a good leaving group, right?
The ozonium good is a good leaving group, right? So absolutely. So when you don't know what's going to happen, what do you do first? Identify who's going to be an electrophile and who's going to be a nucleophile. Right? That's the best way to start if you're kind of stumped. So absolutely, you know that the diazium group's a good leaving group. So boom, you spotted your electrophile. Who's the nucleophile?
The pyrrole.
The pyrrole, yeah. And specifically, make sure
the
you
nitrogen.
catch at carbon.
Wait, what was the question?
The metacarbon.
Yeah, we don't really call it meta when they're 5-membered rings. That's something that's kind of specific to benzene, but carbon 2, which actually I guess would be para, but yes.
Oh, it wouldn't be the nitrogen?
No. All right, so this was the whole shtick about the pyrrole, was that again, it's the ring that's behaving like the nucleophile. Yeah, something that's very different from how amines behave compared to pyrrole. That's partially why we give it its own special name. All right, so again, this one was a little bit tricky, but one of the things you want to remember about pyrrole is that, as we said before, I ruined it and replaced it with the NAS, but it is a better nucleophile, right? It's more reactive in these electrophilic aromatic substitutions. So pyrrole equals good nuke. That's something that's a good idea to have in your head. And importantly, it's that carbon-2 position that's going to be occupied. We made this argument using resonance structures. Remember, if you put it at the nitrogen, you only have one resonance contributor. C2, you have 3, whereas C3, you only have 2, et cetera, et cetera. You can look back in the notes, but we made this argument through resonance structures as to why that was most stable. All right, and again, so then you've identified, here's my nucleophile, and then I know that this whole diazium business is it makes this carbon a good electrophile, right? So that's sort of how you can reason through that. Again, that's why I wanted to do this sort of first here, so we all remember this compound right here. This is how you convert an aniline into a benzene with a really good leaving group. All right, and it's sort of made also powerful by the fact that we know how to generate aniline from benzene by going through one intermediate step. So see if you guys can't do this multi-step kind of synthesis problem for me. I'll actually make it look more like the exams.
Can you use hydrogen gas to reduce a nitro group?
Yep. Oh, sorry. should be a 2 here. Hopefully that didn't mess anybody up.
I was gonna say something, but then I was like, no, he's probably right.
No, definitely not. There should have been a 2 there. All right, so what's the first step?
I converted benzene to nitrobenzene with nitric acid and sulfuric acid.
Yes. So we need to get to nitrobenzene because then we can convert that to an aniline. And yes, nitric acid with a sulfuric acid catalyst will do it. And then to turn a nitro group into an amine group.
Palladium catalyst, hydrogen gas.
Yep, so we're just gonna reduce it with our palladium catalyst and hydrogen gas. And then as we saw before, when you could treat aniline with nitric acid and HCl, you get what? That was awful.
The diazonium thing.
Yep, so that creates our diazium group. And again, when you're seeing this diazium group, you're thinking what?
Good leaving group.
Good leaving group. That's literally the only role it's going to play is a good leaving group. So then I treat it with, some nucleophile here, in this case, a cyanide ion. What's that going to do?
Substitution.
Kick it off. Yep.
Do you need copper with the cyanide?
You do not need copper with the cyanide. The copper, for whatever reason, well, I say that. I don't think you do.
He makes a good point. There was a part where cyanide would react with some kind of copper reagent too.
No, for whatever reason, these tend to work best, and they really are very shady as to why. But I sort of gave you this anion here. Really, it would be, you would use the copper salt of it. Same if you were to use chloride or bromide. They don't really know why, but yeah. Of course, those would do different things, but yes. Okay, and then if I wanted to, how would I do this last step here?
Reduce it again?
We would reduce it. Do you remember how to reduce nitrile groups?
The N2H4.
No, that's how we would chop off a
Oxo group.
Yeah, an oxo group. This is actually rainy.
You couldn't use the palladium catalyst on this one?
H3PO2.
Say it again.
H3PO2.
H3PO2. Yeah. Okay. So that's actually, you would do that with the diazium group. And what does H3PO2 do?
It will remove that.
This is how we chop off that diazium group. So for whatever reason you wanted to take this roundabout way of converting benzene to benzene, that's what the H3PO2 is doing for us. No, I mean, at least as far as I can remember, our only method of reducing nitrile groups was with Rainy. And actually, we got to be a little bit careful, because if we were to use Rainy and heat,
would it just make a methyl group?
No, that is the way to reduce the entire ring. So the only way that you can reduce benzene, convert benzene to cyclohexane is with rainy and heat. So pretty aggressive conditions. Basically, rainy is like the strongest of all the reducing agents. So anytime you have to have rainy, it's because it's a harder group to reduce. I guess it's rainy nickel to be sure. Okay, one more. We got no amount of time, but just real quick. Let's just do this example here. Talked about our reducers. What about our strong oxidizer?
That'll convert all terminal carbons into carboxylic acid.
Yes. Not even terminal. No, it's actually just the ones that are one removed, all what are called benzylic carbons, ones that are one removed from the ring. So in fact, what we would get here, I'll draw it out just for the sake of it. So it actually oxidizes at that benzylic carbon position and effectively then chops off those other carbons, right? You will always get a carboxylic acid group that's just one removed from the ring.
No matter how long that carbon chain is?
Yep, no matter how long it is, doesn't matter. It will always react at the one that's just one removed from the chain, from the ring rather.
I do have one question going back to the other reaction, the diazium one.
Mm-hmm.
There was a problem in the homework where the diazium reacted, but it didn't chop. Like the azium group wasn't a leaving group. It actually stayed, and that reagent bonded to the azium group. Like the triple bond between the nitrogens moved over one.
Yeah, we skipped that section. That section's not going to be on the exam.
Okay, gotcha.
So there was, that was my bad for assigning that problem. But yeah, there was basically a way that you can like join two benzene groups together with this azium connector in the middle. I don't remember, 18-16 or something like that. We didn't do that, so don't worry about that. As far as we're concerned, you see that azium group, you think leaving group.
Understood.
All right, so that about does it. If you guys have any, particular questions or whatever, just make sure to hit me up. Right, I mean, exam on Thursday. Everybody make sure to be there on time. We can't start until everybody's there. So if you show up more than 5 minutes late and I've already distributed the exams, I'm not going to be able to let you take it, et cetera, et cetera. So everybody just make sure you're on time. Keep the exact same format computer-wise that you did for the last exam. Don't be trying to change devices or anything like that. We don't need any like last second curveballs. And take a second to, at the end of today to make sure that you're like in a good position with your camera. Some of you, I was pretty much like looking up your noses the entire exam because it was placed directly in front of your face. So if you can find a good desk space where you can set it back a little bit further than you maybe normally would, that would be great. All right. And yeah, again, if you guys have any questions, we can always like hop on Zoom for a second. I can share my screen and we can go over a problem if you need to.
My computer's kind of touchy. For instance, during the Zoom meeting, I lost connection. It's just being glitchy, and I had to switch to my phone. So I'm currently on my phone.
Okay. So what you want to do, Carlo, is just set up both.
Okay.
So if one of them dies out, you got to back up.
Got you.
All right, so you can follow that same link in both of those on both of your devices, and you'll just be signed in twice, and that's perfectly cool. And then you got some redundancy.
Got you. All right, thank you.
Cool.
I do have one more question about the formal report.
Yeah. You just muted yourself.
Oh, gotcha. For the one of the questions on the discussion section, I'm having trouble answering the one about why condensation occurs without an acid catalyst. Does that have something to do with the pKa?
No, it has something to do with resonance.
Okay.
So look at your product that you would get sort of after condensation, and you should be able to make a stability argument as to why that was like so favorable to be formed.
Understood. Okay.
It's tertiary. No, I'm just kidding.
No, yeah, no, don't say that. All right, guys. All right, enjoy your afternoon. Hopefully it doesn't get hotter than hell tomorrow. And yeah, I'll see y'all on Thursday.
I have a question about the slide before.
Yeah.
Hold
up.
So I'm looking at slide 13 on chapter 19. It's PowerPoint.
13, I don't know what that is. I guess I can figure it out.
Relative reactivity toward electrophilic aromatic.
Oh, I inserted that. Something like this?
Yeah, that's the one. Can you explain how that, how you got the answer on today's problem, or is that related to this chart?
Yeah. So what's important here again, what they're sort of getting at here is reactivity of electrophilic aromatic substitutions. What that's really saying is that all of these rings are even better nucleophiles than benzene. So anytime that benzene can play the role of a nucleophile, they can play the role of a nucleophile too, and they're even more reactive. So here, if we just want to look at this aniline reaction down here, we of course have this good electrophile in our carbonyl carbon. So pyrrole will play the role of a nucleophile and attack that. Well, of course that has to bump up there, but yeah, so basically you have, again, pyrrole playing the role of a nucleophile. And here we have this good electrophile in this acid anhydride, right? In today's example, we again have pyrrole playing the role of a nucleophile, and what I did was give you this compound here where you know that this carbon is a good electrophile, right? So I sort of specifically picked it because I didn't think that it was one that you guys had necessarily seen explicitly before, and you would have to go through this like logic of, okay, well, I know that this is going to be an electrophile, and I know that this is going to be a nucleophile, and thus, bada bing, bada boom. Okay. Does that help?
Yeah. So pyrrole is the most reactive.
Pyrrole is the best nucleophile. Yeah, in terms of like the ring behaving as a nucleophile, yes.
Okay, and pyridine is even more reactive than pyrrole in regards to EAS?
No. Pyridine is less reactive with regards to EAS, more reactive with regards to NAS, nucleophilic aromatic substitutions. So if we were going to put pyridine in our little chart here, pyridine's actually over here.
Okay.
Right? You need to, even to like brominate it, you need to have not only your catalyst, but also extreme temperatures to get it to behave as a nucleophile. But in terms of the NAS reactions, this is going to be the most reactive.
It just reverses, right? Okay.
Right, so like I kind of try to keep them separate in our minds here. The 5-membered rings are always better nucleophiles, and the 6-membered ring, the pyridine worse, and then it's the exact reverse for the NAS, for the nucleophilic aromatic substitutions.
Okay, gotcha. So if you were to, increasing reactivity, so it would go pyridine 1, benzene 2, and then pyrrole would be the most reactive.
For nucleophilic, right? So if we're going to change this to nucleophilic aromatic substitutions, then yeah, all these would be exactly reverse. Right, and the whole idea is that the ring's behaving as a nucleophile. So having a lot of electron density in the ring is good. But if the ring's behaving as an electrophile, having a lot of electron density there is bad. Right, so really the ranking has to do with how much electron density is sort of bouncing around within that ring.
Okay, cool. Thank you.
Cool. Awesome. All right, hopefully that wasn't too confusing. All right, guys, I'll see you all on Thursday. Let me know if you have any questions.
All right, bye.
Bye.